So hello everyone. Well, thanks for the invitation, Yuba. So I'm a Ludovic. Where is Ludovic? Ludovic. Voilà. Yes. Today, what I want to talk about is maybe something unusual for here, or I don't know. It's definitely linked to networks, but related to social network of teams. And I will describe a lot of a huge data set we have on that, and what kind of structures with inferring for the networks, and what is universal, what is linked to high-performing teams. So I'm a researcher at CRI with a physics background. CRI is in the Marais. I don't know if some of you have been visiting. I know some of you have come. We have a network seminar with Yuba on Thursdays that you're welcome to come. And we also have visiting position if you want to come for a short term and explore some interdisciplinary projects. We're always happy to host people. So a lot of things I'm going to talk about are at the big picture level related to a very nice book that I've read a few years ago that's been a big source of influence for me in my research. It's Reinventing Discovery by Michael Nielsen, where he's describing all the recent efforts in the past 10 years to do massive collaborations linked to citizen science projects or to urban science projects. And one thing he describes is that usually these massive collaborations, they're nice, there's ways to use what people do, but it's not generally like very complex projects because people you have a crowd of thousands of people working on the same project, you don't know who to work with, who to collaborate with. And he described that we should soon have a way to design serendipity, to help design the links between people who could collaborate with whom for a research project. And that's something we began to design with an initiative that I'm just going to talk about here called Just One Giant Lab, where we're designing a platform where people can post projects, can connect with other people, can declare their skills, and based on that, because we have this data, what one wants is link prediction, recommendation system of who could you collaborate with so that your project maximizes the output, or so that you can just find the resource you need. And so we began doing this platform 2 years ago, and in order to back up a bit the science of how you should connect people in order to have a successful project, I began several research directions in my team, so that since I'm at CRI 2 years ago, I'm going to talk mostly about the left one today, which is collaborative solving, where we're looking at data related to how people work together in teams and how they share the tasks. So how to describe the task a person's project, networks. I've been working as well on how people innovate in scientific fields, so what type of people and what type of behavior is linked to scientific innovation, and that's something we've been studying with Yuba. I related to the collaborative solving. Here I'm going to today describe mostly teams of 10, 20 people. Now we're looking at teams on GitHub of 500,000 people and looking at how they organize their work, on how they organize the commits and how they, what type of hierarchy you have in terms of the organization of the community. And something I won't talk about today, but we're also looking at phone call data sets in the context of trainings. So that's the collaborative learning part, where we have people following a training, we have the phone call they have between themselves, and we have their performance, what type of answers they gave to different parts of the training in time, and we're looking at epidemiological model of knowledge transmission between those people. So some kind of bottom-up, horizontal learning, and what makes it efficient and what are the network effects that underlie it. So today I'm mainly focusing on this part, but I'm sticking around for a bit today, so if you want to discuss some other parts that you might be interested in, I'm very happy to discuss more. So the collaborative solving part enters a bit the spectrum of the past few years, people looking at very large data sets related to scientific output, scientific traces in terms of, so either the science of what are the publication records of people and who can you predict will be successful, as well as data sets around teams related to just scaling effect with team size. What is the output of a team depending on this team size and what type of, is it a creative output or is it more like deployment, patent style, so something that comes later in terms of a field. Many of these work are based on output, so knowledge output, the team's output, and none of them really look at the process of how people actually, during the project, collaborating and coordinated to deliver the knowledge output. Work has been done for the past 30 years by people like Bruno Latour to investigate, go into scientific teams, sit down and literally look at how people are working together. What are they deciding will be a good research project? Who gets to decide? What is the role of PI versus a team, etc. But it's very costly. It's one full-time investigator for a year in one laboratory. So here what I'm going to describe is a model system of looking at how teams work together. That comes from a scientific competition called IGEM. It's an engineering competition, but for biology. So teams are designing what they call biobricks, which are DNA elements that they combine with other DNA elements to make bacteria that have new functions. So you could compare it to robotics, except that here it's very interdisciplinary. You need wet lab people, so you need experimentalists, modelers, designers, you need mathematicians, you need, like there's a whole spectrum of skills you need in the teams. So they work for 6 months in a lab, and at the end of the 6 months they all meet in Boston for what they call the Jamboree, and each color is a team here of students. It's been happening for 14 years, and there's been more than 2,000 teams participating to it. And the good thing you have is that you have a lot of data that I'm going to describe, and you also have outcomes of those teams. And each team has 6 judges that determines whether they can get medals or prizes or some performance criteria. So the first thing is that it's synchronized. So all of them, they begin at the same time and finish at the same time. So it's 6 months with all the experimental work in the summertime. It's been growing, so I told you it's 14 years. But nowadays you have around 350 teams per year, which is quite a significant number, so that allows us also to control from year to year batch effects. Quite international, so it's all the teams that have participated to the competition, which also allows to control for country-specific effects in the modeling. So data, we have a lot of data. We have, I would say, traditional scientific data, such as team collaboration network. So teams can collaborate with one another, and that creates just an inter-team collaboration network. So we have access to that for each year, and that would be similar to the scientific collaboration network in a way. We also have a citation network. I told you they do biobricks, and these biobricks, these DNA elements they do, reuse previous biobricks from other teams. So it's a bit like a technological flow, if you want, or it's like a reuse flow. And from that you can also build this biobricks reuse network that quantifies and shows how this competition has developed some kind of product space, and also allows to see how do they combine that, how do they make new functions, and what is impactful, because we have the number of times it's reused in the long term, also the success of the team in the short term in the competition. But finally, the most important thing we have here is that we have the notebooks of the teams. So we have what they have done during the whole process of the teamwork. And we don't have the written one, we have the digital notebooks, because they are forced as part of the requirements to use a wiki-based website, where each team, they have their own websites based on the wiki standard. They describe all the notebook of what they did, all the modeling, all the team description. It's like a big scientific paper with a whole supplementary information that would really be explained. And because it's wiki-based, in the back end, you have, for each action, a timestamp of a person, of a user ID, a content that was added or withdrawn, what is the amount of text that was withdrawn or added, and also what text was added or withdrawn, and a comment. So it's very similar to GitHub in a way. You commit each time some text, and we have that for each team in the past 10 years. I will show you some scaling properties afterwards, just to show you 3 example teams, and this is a cumulative activity of the teams from the wiki, and can see already that there's some different ways to behave, and some teams are very last minute in the way they do the work, right? And these are not really much the ones that are going to be interesting for us. But so you see that you have different ways to behave dynamically. So we have that process, but we also can reconstruct a user task network from that. Because the wiki is divided in sections, and each section has an ontology related to an element of work that was done by some people from the team. And just based on the fact that team members can edit the same subsection, we can reconstruct bipartite networks of people to task network that you can then project on either layer, either to have a project space of what are the sections in the wiki that are similar, or co-written by similar people, and you can have an editor space, which is who are the people that worked on similar sections in the team. And that's one team, but you can do that for each team, so you see each time you have a different bipartite network and different spaces of editors and sections. This one is a clear example when you have an actual subgroups in the team that have worked, but that the subgroups were supervised by one person in the middle between the two subgroups. And final thing we have in the data is performance metric. So the performance metric, for each team you have 6 judges. It's actually quite impressive. They have to grade 60 criteria from 1 to 5. Criteria are, is the project creative? Is it impressive? Did they fulfill? Did they make a new biobrick? Is it like they have 60 different criteria that are annotated. For having medals, they just need to have fulfilled some of the criteria, like collaborating significantly with another team, or there's a list of them. They can have special prizes, which is more like, are they really good at, for example, making a software or making a biobrick? And the winner is more, was it really an impressive team? So the winners of IGEM, the work they do, it's a PhD level, like good, impactful paper level. I've been there a few times and it's really impressive.
Like what?
Like they make a new species of rice that is like, resists everything, and that they have tested, that they went to local stakeholders and worked with different like municipalities in China to put it into place. And like in 6 months, they basically have done a 5 years European grant because they're 25 on the topic, working 24/7, and they have time. But yeah.
Maybe they have started before.
And usually they also tend to start. So the earlier you start, the better, and also the more. Well, you will see what predicts. But yes. So overall, that's the landscape of the data set. We have internal networks, team-to-team network, citation network, or biobricks network, and some success measures. And so what interested in that particular data set was to go to all these teams we have, and we're going to be able to measure many features of these teams, like many things related to the structure of the network, or to the size of the team, or many dimensions, and some of them will be correlated. But that provides you some kind of space in which you can imagine that teams will sit somewhere in that space. And that somewhere will be determined in the first part by some kind of universal aspect of how teams, what is something shared? What is something that is almost just shared to human coordinating each other? So they sit in a space, and in that space what we have is, in biology you would call that a phenotype, but it's that some teams, they tend to have a higher performance than other teams. And so that gives you some regions of the space that as a team you want to go towards to be high performance in that competition. And the final thing I will talk about is that space, because of the fact that the competition runs each year, as a team you can re-participate. And so you can look at the learning, the collective learning at the level of the team of what did you improve over in terms of the feature, and what is your trajectory in that space, in that feature space.
The members of the team remain constant over time?
So you typically have 20%, like the core, that remains, and the core will be, so there in the team you have PIs, instructors, and students. Students do the work, instructors advise, coordinate, help. PIs are here to be a name holder and to also say, I have this lab, we can do bacteria, you're going to do bacteria very probably. So So yeah, there's a structure.
For the evolution, how many years do you have in the data?
From 2008 to 2019, so 10 years, yeah. So what I will show data for 8 reparticipations. Actually, well, it's in the little thing, but that's the data. And especially this one, so a lot of things. My goal today, I'm going to show you a lot of things that I found in this data set. But one thing that we are still lacking is a good modeling of the generative processes that explain these particular features that I will show you, or the way the improvement works throughout the year. And there are typical process that you can do where, depending on the number of people you have kept from the previous years, and depending if you have also survived, because there's also a selection bias that if you didn't succeed before, you're not reparticipating. So you want to quantify the survival and the selection bias as well as the learning and height occurs. I will show hints about how we think this is happening. Okay, so universal, I don't really like saying universal, but let's say that this is, you have some kind of steady state regime and they're fluctuating around it. So that's the typical sizes we have, the distribution of team sizes, and it's on average we have a size of 8, and you will see later, but we're mainly interested in larger teams, larger than 10 people, where it begins to be hard to coordinate without some kind of structure of organization. And so we have data from the wiki edits, and they're pretty stable across years. This is all teams from each year, and so we have around 800 wiki edits per team at the median level. And it's stable across competition, which gives us a good case to using all the data to make a prediction. Activity dynamics, so I've shown you this slide before. I would say this one is a fun item. Well, you can see here that there's a deadline effect, right? It's not very stupid to think that one would want to try and quantify that. I don't know if you know this paper, but there was a Nature Physics on deadline effects a bit more than 10 years ago, where, I mean, the only thing they did was to record how many submissions to a conference they were having, and they saw that the number of submissions to the conference was following a 1/t minus t star, where t star is a deadline time. And it fits very well. And then they did that also for the payments, and you can see that there's a scaling exponent which is much, much stronger, because nobody wants to pay, right? You submit abstracts, but you're really waiting until the end to pay, right? And so they have that over, you know, like one order of magnitude, like it follows well from 0 to 60 days, so yeah, maybe 2 orders of magnitude. So I did that on a log-log scale in our case, just to see the scaling better. And we actually have this deadline effect, but for 5 orders of magnitude. So literally until the last minute that you can edit the wiki, you will do it, right? And you will do it in a more and more pressing way. And the exponent is 105, which is pretty impressive in terms of keeping close to what people have looked at. I still don't know why it's so close to 1, but so that's one thing that is at least recapitulating something known about how people behave with deadlines. I'm quite impressed it's hold until 100 days to the minute.
You mean scaling? Why scaling is 1? Minus 1?
So yeah, the exponent is 105. So the exponent of this red line, which is the fit from 100 days to 1 minute, is 105. And what they had for the journal, for the conference submission was 1. And I guess, I didn't put the standard deviation of 105, but you're pretty close to that. So we have a deadline effect, but I really wanted to talk about networks, and especially because these are things I'm interested to find some generative models for, and that's one direction we're exploring now. This is what's in network. I represent it always as bipartite network because I don't want to project it and assume anything about what the social network structure should be based on that. The bipartite is that you have people editing sections. They can either edit alone, this is gray, or they can edit with someone, this is red. And the bigger red points are collaborated by many people, more than 3. I did that for reasons that will be clear after, because you can already see that there is some kind of nested structure. I will talk more about that after. So when you have a bipartite network, you can begin by looking at each layer and what kind of statistics you have in terms of the degree distribution of the layer. First, here the layers have a strong meaning, so if you look at the editor layer, the statistics will be the productivity, how many sections you've been involved with. And so if you do the distribution, it will be the workload distribution. If you rank editors by how many sections they have done, the way the distribution looks will tell you whether people tend to work equally on as many sections than others, or if it's unequal. Some people take all the load and others don't do a lot. And obviously, because you've seen the network, you know that some people do many sections and some people don't do many sections, so we don't expect it to be equal. I'm just going to show straight lines, so I'm going to log the y-axis. So we did that for teams of different sizes. So from size 2 to size 36, each color or each line is average over teams of that given size. So blue is the smallest team and red is the largest teams. What you see is, the reason I logged the y-axis is because there's an exponential decay. If you actually take into account the differences of team size and normalize the rank of the editor, you actually see that all these teams, or all these team sizes, collapse on this one exponential family, or one exponential line, and the exponent of these lines is pretty well conserved, especially for teams above size 10. So that hints of one aspect that looks shared across teams of very, very varying sizes is the work inequality distribution, where you have this exponential decaying distribution as a function of your percentile of workload in the team. On the other side, we focus on the sections themselves. Sections can be edited by few people or many people, so we can rank sections by how much they've been edited or how many people edited them. And if everyone does their solo part, it would be flat like that. If many people collaborate on sections, that would be something close to 1 in the beginning. And when we do that, so this time we need to normalize the y-axis, which is the number of editors collaborating on sections, because obviously teams have different sizes. And so if you normalize by the top section here, what you see on this layer is that there are two things. There is a part where people collaborate on the top 50 section, and then there is the solo section. And it looks like for different team sizes, you have the same structure on collaborating on a core set of sections, and then going back to solo writing. And so if you mix the two layers together, one thing you can then look at is then how, so not just the inequality distribution, but then how nested the network is. And in that context of nestedness, it would mean that you have kind of you see it in the layout as like an embeddedness where the central most written sections, most edited section, or with most collaborative sections are in the middle, and then you have least collaborative sections as you go to the periphery. So Russian. And that's something that I've looked at because that's a type of analysis you do a lot in ecological networks, where you have bipartite networks. Typically, you have pea-flower networks. And what you have, what is called nestedness, is the fact that specialists are interacting with generalists of the other layers. And that's something in ecology that has been shown to be selected for evolution, probably because these type of mutualistic networks are more likely to persist over time. That's triangular shape of an adjacency matrix, typically. So it's definitely something. So it's something where if you do something alone, you'd better do it on something that relies on many, many, many other people, because that thing is highly probable to survive. So I'm going to show x, y axis. So I'm going to show it in our case, but plotted like that. And so if we do that to the section to editor level, and if we rank editors by generalist to specialist and section from generalist to specialist, we have this shape. So we average over all teams, and for each team we compare to a randomized matrix to compute a z-score, an enrichment of a particular cell compared to a random matrix. And what you see in purple is regions that are enriched, and in white is regions that are less enriched than would be expected. And here what you see is that we have a more triangular shape than would be expected. So especially specialist editors are much more likely to do generalist section, and specialist section are more likely to be done by generalist editor. So we retrieve this effect. It can be quantified. There are ways to compute nested temperature, proximity to the most nested matrix you can get, and compare it to null model where you basically do random matrices with same layer degree distributions. And so we have lower temperature, which means more nested teams or more nested projects than would be expected with a random model. So that's for the team network, and as I told you, teams also collaborate with other teams, and that's the last kind of shared structure I will show you. We relate them because they can mention each other in their wiki, so that allows even to actually have a weighted network in how many times we mention another team. And we did that for all years we have in the data. So these are the collaboration network for each year. You see that there is a change happening around here where the density increases, and that's the number of isolates you have in the network. What you see is that at some point they changed the criterion of collaboration to be a requirement for gold medal to silver medal. And what you see is that this change of requirements, this change of incentive completely changed the way, the way the network looks. Like it changed at least the fact that newcomers would be connected with someone. So that's an effect of incentive. But what's interesting is that if you look at the strength, the weighted degree distribution for each year, so you see indeed that the average strength, so the collaboration was incentivized throughout the years. But if you look at the exponents of the tail, it's been actually pretty conserved throughout the year. And if you were to just rescale each of these collaboration distribution by the average strength, what you see is that even if you incentivize to collaborate more, that doesn't change at all the way teams, the inequality between their collaboration. Some will have 3 decades or like 2 decades more stronger collaboration than others. So that's for that part that is about the kind of shared aspects of how these teams operate in IGEM. What I wanted to show now was what makes them better, what makes some of them perform better in the competition. So the first thing I wanted to show you is that the judging quality the judging has pretty good quality. So if you take teams that have no medals, and if you look at certain features here, such as the team size, or the number of sections they did, or the productivity per capita, or the number of biobricks the team did, or the number of instructors of the team, they all have some pretty nice linear scaling with the performance of the team. So here it's no medal, bronze medal, silver, gold, having a grand prize, or being a winner of the competition. And that's, well, one thing is that first, these are features that are of interest to describe the team performance in the competition, but also it shows that there's a good quality of the judging data, which is for a large part based on what appears in the wiki. So that's one thing about kind of self-consistency, but because you have that on features that are pretty obvious to look at, then you can go to features that are not necessarily obvious to look at. So first thing about temporal dynamics, this is the activity of teams throughout the year. So this is each gray line is a team, and the black line is a typical, like the average activity of a team. As I told you before, they're all pretty much synchronized, so whatever your medal is, you will have more or less the same activity throughout the year. What is known now, and what is not shown here, is that you can have different ways to organize your work. You can be regular in your organization, or you can be bursty, so you can have different inter-event time. So typically, you would say for the same average activity, you can have something that will be more based on regular dynamics of teams, or bursty dynamics, and it's been shown already that high-performing teams have a more bursty dynamics. So what we're going to look at is the inter-event time distribution. This is the inter-event time distribution. All gray lines are all teams. The black line is the average. And this is if you then categorize teams by their final performance in the competition. What you see, the black line is no medal and blue is winner. So you see that the blue is approaching this scale-free distribution. And that's something you can quantify with the burstiness coefficient that was introduced 10 years ago that looks at a departure from Poissonian. You can just recapitulate the fact that a high-performing team have a more bursty behavior in their inter-event time. So that's something that was known. We also looked at the other quantities I've shown you before. So I've shown you that there is this tendency to have an exponential workload in the editor layer. And if you classify by performance of teams, what you see that this is true whatever your team quality was. What is just making a difference is how many sections you've done. So it's not so much how you organized, it's more how you organize the workload. It's just the quantity you've done that matters. But what I was interested in was how people have collaborated. So even with the same inequality of workload, how did they collaborate on collaborative sections? And in this one, what we found was that the teams that are winning the competition tend to have a denser collaboration core. So what I call collaboration core is the set of sections in the middle that people are collaborating on. And this is, here I show you teams of same size and same number of sections to compare what is having a high collaboration core with a low collaboration core in terms of visually comparing. So high collaboration core is that people overlap in a lot in what they have edited versus a lower one, which is not overlapping a lot. And that's something you can quantify by just looking at the, here I just looked at the area under the curve in the top 50 section for each team. And that's an effect that you can then look, and typically you can make linear models where you look at like team size, number of editors, number of sections per editor, and you can add this collaboration score, and the significance of that feature kicks in for teams that are larger than 10 individual. And small teams typically more rely on team size or productivity to actually perform in the competition. So that's for the collaboration. And the last thing is the nestedness. So I've shown you that teams tend to have a nested architecture. That's something for each team you can quantify with the z-score. So you can compare the team nestedness temperature to the one of the null model made out of randomized matrices made from the same degree distribution of that particular team. And that's also something that associates with the performance, and that you can also do a linear model to explain the outcome, the team performance. And you find that for large teams, so this is for teams larger than 10, it's not, if you control for size and productivity of the team, what actually predicts the outcome will be this collaboration feature and this nestedness of the structure. So these were basically examples of what type of fluctuation, or what direction teams are trying to optimize for higher performance. But here we have reparticipation data, meaning that we can actually track teams across competition. So here what I will show on the x-axis is the number of participation of a team. So first participation, second, third, fourth, etc. And on the y-axis, what I will show is features normalized for the particular year the team participated in. So I will show z-score. So for each year, I take all the features, say for example outcome, which is 1 to 5, no medal, bronze medal, silver, gold, prize winner, 1 to 6. And I just standardize it so that I can compare from year to year in case there would be feature changes. And here, this is the data average across all teams that participated the first time, second time, third time, etc. So the first thing you see is that there is an increase in performance in the team that will participate. So it takes 2 years to perform better. There are biases in the way it works. So if you began with no medal in the first participation, you will actually never reach the same level that if you began with bronze, silver, gold, or above. So that's a way, for example, to look at lock-in effect, the fact that the initial success will determine how far you can get afterwards. So there are some features that will not allow you to navigate the whole space. Then you can look at different features that are found to be predictive of the medal. Here what I show is the way the feature changes, and I showed, like, these are regions that correspond to the average value and 2 standard deviation of that feature for teams that didn't have medal and teams that won the competition. So that allows you to see that some features teams are able to improve over them to the level of winning teams. For this particular feature, that's an example where this improvement doesn't depend on your initial success. Whether you had no medal, bronze medal, or prize medal, you have the same trajectory of improvement, you have the same slope. This is true for a few features, like the size of your wiki, the number of sections, the productivity of the teams, which is the number of biobricks. And then there are features that that have a lock-in effect, so that have a dependency on the initial condition, typically inter-team collaboration, your ability to collaborate with other teams. If you didn't have a medal the first year, you're never able to find partners with whom to collaborate with other teams. So there's a lock-in effect here that is one that can explain the performance lock-in effect. And you have also some features that teams are not able to change, even if these features are predictive of the performance. Number of instructors or the intra-team collaboration networks are things that are just not, well, I guess not easy to change. Number of instructors is very much contextual, and team network is something that is also very hard to visualize or understand or incentivize to change. So to summarize a bit, so we have this idea of looking at how teams change the feature in time. I tried actually to make a representation to just visualize what that actually means. If you take all those features I've shown you, you can simply do a PCA. Actually, on the few features I've shown you before, it ends up having one component that is very predictive of the end outcome. And so here all gray nodes are team. I highlighted in black no medal, and in blue the winner of the competition. And then if you just focus on this black and blue, and you take teams that have failed initially, so that didn't have a medal initially, but that ended up participating more than 4 times, you can visualize the average trajectory in that space and see that allows to see a bit the way these teams improve and the way they navigate the future space to go to the winner region. So the purpose here is not to have a real true trajectory, but to kind of visualize what this looks like, and ideally one would want to understand there are some dimensions that are constraints that you can't move along, like number of instructors, so that they constrain the way the trajectory can move. So that's the direction. So to summarize, on this data set we have a lot of teams, more than 2,000 teams to explore teamwork and performance. We look at learning and have a lock-in effect that we try to explain through that some features are not able to move throughout the learning process. What we are trying to go towards now is having models of what processes in terms of teamwork can explain the observed phenomena, and we're also doing a project now to collect real-world social data in those teams to actually confront them with the digitally obtained data. What we're doing is that we're coding an app, we're developing an app that can access the Bluetooth of the smartphone to map the proximity of people in the lab. And in this app, we send notification to journal the tasks they're doing, with whom they're doing the task, and also longer questionnaires. Okay, well, that's, I can jump a bit. And typically, the kind of thing we can do with this questionnaire is ask them to nominate people related to who they work with, who mentors them, who they trust, so empathy layers. And so we had a survey last year on 79 people spanning 19 teams. And we're doing now an approach to look at the multi-layer structure of these teams in terms of the different layers of their social network interactions. That's an example of what we're having with one layer, which is who is in your subgroup. So we ask people to nominate who's in your subgroup, and the color here is colored by the two communities of who did you know before. So we can see that, for example, in subgroups, they mix people that knew each other before, that there are people that bridge subgroup, and we're doing things such as looking at the learning effect. So we ask them who is sharing knowledge with you, or who is the leader of your team, and these tend to be people that participated before in the competition. So that allows to see that there is a role in the knowledge transmission from those people with prior experience that is directly seen in those networks. And we're also looking at layers in terms of explaining models of how do you connect based on trust or empathy. So we have strong gender, for example, gender bias in terms of who you select, who you nominate to in the trust layer or in the empathy layer, but there's no bias in the subgroup layer or advisor layer, showing that these teams have different, social space in terms of interaction, and workspace, which is a subgroup, and that's something we're interested to correlate with the data we're going to have in terms of performance to see if there is a mismatch between the two, how they can affect the team. Okay, maybe to finish, we're doing similar analysis now, and that's something I talked in the beginning, on open source communities, because we can describe the same bipartite network of people to the files they have committed, and it's also dynamic, and you have a lot of performance metrics, either the number of stars, or the number of forks, or the survival of the project. So we have that on 7,000 GitHub projects, and we're looking in particular, we found that there is a nice scaling property that once a repository is big enough, you have scale-free distribution of the workload inequality. So they converge to some kind of organizational structure that looks very self-organized. And we're also implementing on Just One Giant Lab, on the platform I told you initially, we just got a grant, a funding, to test notification and how they influence the way people connect and the way people post projects and document their project. And here we're literally testing the implementation of designing tools that allows to accelerate projects. And it's a collective intelligence grant, so it's really devoted to testing that we can foster collective intelligence by acting on these communities. Okay, so this is the few people that have been involved in those projects. The team project started it when I was doing my postdocs in Boston, and Ratin is an intern that is working on the survey network. And for the app development and the questionnaires, we have a lot of development team and a PhD student and a postdoc, ex-Ipsys postdoc, working on that. And yes, that's all for today. Thank you. So it's a bit different than the review process because here they have 60 criteria, and the way they grade each criteria is they're presented sentences. Like for example, how creative was the project, and they have to choose 1 out of 5 sentences like the project didn't show that it was able to do that, or the project showed some elements of that, etc. So they actually based a judging system on a handbook from 2013, I think, specialized in how to make judging the most objective possible. What I'm trying to get access to is the actual judging grade, so that then I can look at variance between judges, inter-judges variance, so that you can then remove outliers, for example, out of judges that are just nonsensical. But if you have access to that, you can go for each criteria, and I expect that creativity would be one, for example, that would be high variance, whereas how you perceive the project is the simple one to answer, maybe. But we're trying to get access to that.
Yeah, but how expert are the judges?
So judges typically, it's like in conference panels. Either they're ex-participants or they're just experts in the domain. So they go from, usually they're minimal PhD students, that's the minimal level they are in the field, from PhD students to above. And yeah, right now, I'm just waiting to have access to the judge-specific data. That's why I showed this first data on the fact that it's pretty predictive of some obvious features of team productivity, and that's why we can at least have some confidence in aggregate measures using that criterion.
Just a question. At the moment in your presentation, you showed two PCA showing what is the successful team and
yes.
the loser team.
Yes.
But you didn't really elaborate about what is the meaning of the three axes. So what are the interesting features if I want to be a winner or if I want to be a loser?
Do I have it in that slide deck? I don't know. Let me look, because I have the linear model somewhere with everything. Let me see a bit. Well, maybe this one is a bit old, but it's not shown here. Because I recently added new features, so I think it's a bit outdated. But what was this one showing? Let me see. The first thing that we had in the data set is that it depended on small teams and large teams. So we have around a threshold of 10. We have a stability in, for example, how many people in the team collaborate on sections, or like what proportion of the team is collaborating, etc. So we had good reasons to see that the large team was more network-oriented and small teams was site-oriented. So we did some linear models controlling for years, location, type of students. So these are all controls, and these are some features that we used in the model. And for small teams, the features that were explaining the performance of teams was the team size, the number of editors, the time spent, so the number of days, so wiki had an edit, the number of instructors per student, so the kind of supervision, that was specific. So these ones were specific to small teams, and shared with large team, you had the number of biobricks produced, which is an engineering competition, that's what you have to do. And the prior experience, which is a control, kind of. It's did you have success before in the competition? It's kind of controlling for the learning.
And so, for example, for small teams, it's better to have, I guess, a small team with experienced people. I don't know, because you say the attributes, but
for small team, it's better to be a bigger team.
Okay.
But if you're not a bigger team, for small team, then you want to spend. Basically, you want, like, it's a man-hour thing, right? You want, if you have less people, you want a lot of time on them, right? So this one is man-hour, and you want also to have. So the thing is that it's a linear model, so it's hard. It's not a decision tree, but yeah, one could do a decision tree to have a more granular aspect. So if you're a small team, try to get bigger, and that's not so interesting actually, because many small teams are small because they decided that a few people would edit the wiki. But for big team, most of them, everybody's editing the wiki, so they're more representative, the wiki data of what's actually going on. Here we have wiki quality was actually a name to say number of edits per person. So it's individual effort. So it's kind of individual productivity, number of supervisors, and these are number of collaboration with other teams and intra-team collaboration network. So these are network related, and output biobricks and prior experience. So if you're a large team, the network part kicks in that doesn't kick for smaller teams. So it's I would say some of them are very Ideally, so what I would like to do, because we didn't try to go too far in the prediction aspect in this model, but here the typical things you do is structural equation modeling for this type of thing, where there are features, sets of features that are quite correlated with each other, and you want to summarize them in a latent variable that would be team organization, wiki production, whatever, and then look at how these latent variables are explaining each other and explaining the final performance, which itself is also drawn from some proxies of what the actual performance is, right? And yeah, so that's what we're trying to do.
Some like these like empirical questions. For example, if you have an event of kind of preparation attachment where given that there is a success, the team grows because there are more people like
Exactly.
or another issue that you could see is, for example, what are the effects? Okay, you saw the lock-in effect, but is there that lockout effect? Is that successful?
Because they become too proud.
Either too proud or they don't care anymore. So they just.
So it's not really what we see.
No, I'm asking.
Yeah, exactly. No, but so that's a good question. So there's something that you can look at is the survival of, for example, the teams that have never had any medal ever. This is their survival in the competition. This is the proportion of this type of team you observe as a function of number of participation. This is the one that had, at any time, they just had a bronze medal, which is not so good. This one, at any time, they had a silver medal. So all these are just some kind of minor setback. It's like yeah. So, but if you had a gold at any time before, or if you were a finalist any year before, right? So that's the thing of you have two effects that we need to disentangle here. You have one effect that is the selection bias. You select teams that are better, but that's also this drives better people to them, and that allows to change their feature better. So it's hard to actually disentangle the learning effect from the selection bias. And I would love to have a way to make more causal statements related to that. And because we have some temporal data, it's not fine-grained temporal, but we have some temporal data, so I'm sure there's a way to get that, but I'm not there yet. So, but you see that there's these three aspects that are core.
So that means that the team with low success keep coming back at it, even though the chances of getting better is going down?
Well, so the one with success, you're saying? Yes. So what's happening with those ones is that it becomes almost like IGEM in universities. This is a very, very demanded internship to be part of, because you get a startup experience, kind of. You get a really cool interdisciplinary experience. You get to go to Boston. So it's very demanded, meaning that if the team had success, they're also able locally to get recognition from the university that will set a pipeline for them to do it again every year. So there is some kind of effect of this prior success that is quite important in the stability of them. All right, I'd love to discuss Bluetooth also.